And here we're going to look at waves in a little bit more detail. So we're looking at a mechanical wave. This is a string. Let's say a string is strung up between two sturdy objects, so we can put tension on the string. Then we displace the string just one time, and then the wave created will then rush across the string at some velocity v. The question is, what is that velocity v? And that will of course depend upon the tension in the string and the mass per unit length. So we use the letter mu for that. The mu means the mass per unit length of the string, how heavy or how massive the string for each length, for each meter, for example. All right, notice that here we draw a snapshot picture of the wave. There's just one small wave moving across. Let's say at some point in time it's at the edge of the wave, it's at this position right there, and then in a small amount of time dt, it moves from this position to a new position, and it covers the distance dx right there in an amount of time dt. Notice that the displacement dx can simply be expressed as the velocity times dt. And then also notice that if we take this small little corner right here, the very edge of the wave, and we increase it in size right here so we can look at it a little bit more detail, you can see then as the wave is moving to the right, you can see that then the string will start moving upward. And the velocity of the string moving upward will have a velocity in the y direction. And you can then say that the displacement dy can be said is equal to the velocity in the y direction times the dt in just the exact same way. Now, if we want to get the ratio of dy over dx, what is that equal to? Well, because of this definition here, we can say that dy dx, by definition, is the velocity in the y direction times dt divided by the velocity in the x direction of the wave times dt, and the dt's cancel out. That's simply vy divided by v. Now you may say, well, why did I do that? Well, we also can look at this in a geometric way. This is a triangle, and so we can say that the tangent of the angle theta, this angle right here, is equal to the ratio of the opposite side over the adjacent side. This is equal to dy over dx. And since I defined dy dx over here as this ratio, and again subsequently that ratio, we could say that this is equal to vy over v. All right, so that means I can write that the velocity in the y direction be expressed in terms of velocity in the x direction, the velocity of the wave, times the tangent of theta. Okay, why is that important? Well, you'll see in just a moment. The next thing we're going to do is we're going to think of this as an impulse. This wave, this piece of the wave right here, this small section dx, will feel an upward force because there's tension on the string. So since the tension is acting in this direction, and then the wave is being displaced, it will feel a force in the upward direction. So we can say that the force in the y direction is equal to the tension times the sine of theta. Notice, of course, that the tension will be going along the string in this direction. So the tension will be like this. Tension, this is angle theta. So the tension in this direction is the sine component of the tension. So this will be tension times the sine of theta, which is therefore the force in the y direction. Now, the impulse can be defined as force times time. And of course, if we're talking about a very small amount of time, we have to write it as a very small dt. So this small little section of the string, in the amount of time dt, feels a force in the upward direction. So the impulse can be written as, this would be force in the y direction, as the tension times the sine of theta times dt. We can also say that the impulse is a change in momentum. So the impulse is a change in momentum, and momentum, of course, is mass times velocity. So this is equal to the change in the mass times velocity. Now the velocity is constant. Velocity is constantly moving to the right. Therefore, the velocity in the upward direction will also be a constant. And so we can say that this is equal to v times d delta m. Now, of course, the v we're talking about here is the v in the y direction. And delta m we can write as dm, so this is v sub y times the small amount of mass of the string associated with this small little segment right here. Okay, now we can set the impulse, t sine theta dt, equal to the impulse as a change in momentum, which is vy dm. So now we can go do this. We can say that the impulse causing the string to go up is equal to the change in momentum of the string. So the tension times the sine of theta dt is equal to v in the y direction dm. All right, so next what we want to do is realize this, that the v sub y, which is v tangent theta, appears over here. So we're going to replace what that is equal to with that quantity right there. So this is the tension times the sine of theta dt is equal to the velocity of the wave times the tangent of theta times dm. Now here we need to do a small mathematical trick. What we can see is that this angle is typically very small, right at the very edge. That's a very small angle. So we can say that the sine of an angle, if it's small, is equal to the tangent of the angle. So they actually cancel each other out. So we can say that this is equal to each other for very small angles. So now we can say that t times dt is equal to v times dm. I'm trying to find out what the v is right here. What we need to do now is bring that equation over here. We go t times dt is equal to v times dm. So we need to get rid of the dt and dm. Now dm is the mass of the small little section right here. And remember that the dm can be found by taking the mass per unit length and multiplying it by the length. So in other words, if this is true, we can say that mass is equal to the mass per unit length times the length. And so that means that the dm must be equal to mu times a small segment dl. Of course, in this case, our small little segment dl is actually our dx. So we can write this as mu times dx and plug that in here for dm, which we moved over here. So now we have t times dt is equal to v times dx. Now I'm going to bring my dt over here. So now I get t is equal to, oh, I'm missing something. It's v times mu dx. Can't forget my mass per unit length. There we go. So now we have this as v times mu times dx dt. Now, of course, what's the definition of dx dt? That's, of course, the velocity in the x direction. So we have t is equal to v times mu times v again, or t is equal to v squared mu. So since we're looking for the velocity of the wave, we're going to solve this for v. So we have v squared is equal to t divided by mu, right there, by dividing both sides by mu and turning the equation around. And finally, we can say that the velocity of the wave is equal to the square root of the tension of the string divided by the mass per unit length. So maybe we can write it like this: tension divided by the mass per unit length. And that will be the velocity of any wave on the string. It depends on the tension and the mass per unit length in that fashion. For example, if we want to do a quick example, let's say that the tension is equal to 400 newtons. Let's say that the length is equal to 2 meters, and that the mass of that string, let's say, is equal to 10 grams. Okay? A string that is 2 meters long, has a mass of 10 grams, and is attached in such a way that there's a tension of 400 newtons on it. How fast will the wave move on that? Simply plugging that in. We say, well, that is equal to the square root of the tension, which is 400 newtons, divided by the mass, of course, converted to kilograms, and 10 grams is 0.01 kilogram, and divided by the length, which is 2 meters. And so that's how we can go ahead and find the velocity of that wave. So we have 400 divided by 0.01, and multiply times 2, because when we divide by 2 in the denominator, that's like multiplying by 2 in the numerator. Then we take the square root of that, and it looks like it's 283 meters per second. Okay, and lots of examples of that. For example, guitar strings, piano strings, things like that. We pluck the guitar, and the wave will travel back and forth in the string, typically very fast. And that, of course, depends upon the mass of that string, how much tension we place on it. And we'll talk more about strings and musical instruments later. But again, a quick review here. If we want to find out how fast waves move on a string, we take a quick snapshot at the very edge of the string. We notice that a very small piece of it starts rising up at velocity v in the y direction as the string moves in the x direction. So we can relate the angle to the displacement in the y divided by the displacement in the x, which is the ratio of v in the y divided by v in the x. Then we go ahead and use the concept of impulse. impulse is force times time, or impulse is change in momentum. If we set those two equal to each other, we get this equation right here, and then realizing from this relationship, the geometric relationship between the angle, the tangent of the angle, and the two velocities in the y and the x direction, we can replace the velocity in the y direction by that, and then we realize that the sine and the tangent cancel out. We then simplify this equation. We still need to get a dm, which we can find right here. A dm is simply the mass per unit length times a small segment of length, which we call dx. When we make that exchange, we can then say that we have a dx dt in the equation, which changes the velocity. Simplifying that to v right here, taking the square root, and that's how we find the velocity of the tension on a string. Now, for most of us, we don't really care how we got to that result. It's kind of nice to see how it's done, and some of us, I guess, we are required to figure that out. But then once you have this equation, then it's really simple to find the velocity of any wave on any string, as long as we know the tension and the mass per unit length. And we'll show a few more examples of that in the next few videos.